Hello everyone, here with another lesson for y'all today. It's going to be on a special type of function called exponential functions. So just a review of the other functions we've talked about linear functions. And so linear functions took the form y equals mx plus b. The m was our slope, the b was our y-intercept, and we found that if we wanted to graph this thing without looking at all our x values, finding our outputs, tracing that line, is realizing that our b gives us our y-intercept, our m gives us our rise over our run, and so we can easily graph that as a constantly increasing line. Next up, what we had was, let's let that go. We had our quadratic functions. We talked a little bit about this one last time, and we're actually going to see a lot more of these of our friends during this next unit. But this one had the form ax squared plus bx plus c. So we found out we could factor it using our cross method, or we could use the quadratic formula to find the x-intercepts, or the value of x when y equals 0, which is why we were setting it equal to 0 in our last activity. Okay, that was talking about the x-intercepts, or where they cross the x-axis. So if we were to graph out this guy, we would have something that looks generally like this. Okay? And this is called a parabola. So we have a parabola, we have a line, we have linear functions, quadratic functions. For exponential functions, though, we call it exponential because we have the input, our x value, in the numerator. So if we were to show the equation, it would be y equal to a times b raised to the power of x. So notice how our input is in the exponent of rb, and so that's why we call it an exponential function. Be clear, I want to be clear though, a quadratic function is not an exponential function. Notice how the exponent here, the leading exponent, is 2, but here we have x. Big difference. So just the different parts of it, I told you that the x was our input for our rule. We go through these, we raise our b to that input, multiply it by a, and we get our output. And then in here we have our initial value. We'll see that this is actually our x-intercept, or our y-intercept, apologies. And that the b is going to be our base, or we call it the multiplier. It just tells us how our function grows. So this is the general form. We're going to do an example of plotting this to see what this function would look like as, just see an example of it, what it would graph like. So in this example, we're going to have y equal to 2 times 3 raised to the power of x. And so before we start this, a good thing to note is that if you have a value to the negative power, that's just 1 over that positive power. We talked about this day 1. I'm just bringing it back for you right now, just because we're going to be seeing an application of this right now. So before we even know how to graph anything like this, we need to make our XY chart. Choose some inputs, get some outputs, we'll be good to go. So we're gonna do just that. Gonna have an X value and then a work value where we're gonna plug it into our equation, and then finally our Y value. Okay. So let's start off with an X value equal to -3. That means our Y value is gonna be 2 times 3 to the -3rd power. But let's remember that 3 to the -3, we want to make that positive. So this is 2 times 1 over 3 cubed. So 3 times 3 is 9, times 3 is 27. So it turns out Y for this is 2 over 27. So a really small value. So let's keep going. We'll do a -2. Again, 2 times 3 to the -2 power, or use the reciprocal rule. Put it in the bottom, we'll find that this one's actually 2 over 9. Still a small fraction, but we're getting bigger. Next up, we'll have -1. Put that into our equation, we get 2 times 3 to the -1, or 2 over 3. 2 times 1 over 3 to the 1, or 2/3. So 0 is an interesting one. For 0, we'll actually have 2 times 3 to the 0. Anything to the 0th power is going to be 1. So any value to the 0th power is just 1. So this just comes out to 2. That's why we say that our A is our y-intercept. When x equals 0, our y is just whatever that value is. So we're almost there, just doing a few positive powers. So 1 is 2 times 3 to the 1, or 2 times 3, which is 6. And let's just finish it off with 2. So 2 times 3 to the 2nd power, 3 times 3 is 9, times 2 is 18. So you can see how this thing gets really big really fast. Only in the span between 0 and 2, we went from tiny fractions to a big 18. So we can graph this out. Values, we got some y's. -3. So when x equals -3, y equals 2 over 27, so super tiny. When it's equal to -2, we got 2/9, so again, very tiny, a little bit bigger. Then we have -1 is 2/3. Then when x equals 0, we're up to 2. And then we're up to 6 for 1. So we're already up here. And then 2 is all the way up here at 18, so it's going to be way up here. I'm not going to do that, just to keep the notes nice. So our function is generally going to look like this. Notice how it skims across the x-axis and it shoots up. Another thing I want us to notice is that we have our multiplier, because notice how this is multiplied by 3 every single time. This is telling us that our function is growing exponentially. So there's actually kind of a comparison to our linear functions. Notice how our linear functions add by a certain amount every single step. So our exponential is actually the one that multiplies every single step. So the last thing to really talk about is increasing or decreasing by a percentage. It's useful to know this for like compound interest, for anything that's showing exponential growth by a percentage. So if we want to do that, we have to focus on the multiplier. What you do is say if you're going up by x%, you're going to just add that to as a decimal to it. So it would be 1 plus x over 100. So for example, if we had a value going up by 7%, that would be shown by our b as being 1 plus, sorry, that would be 100, 100 plus 7 divided by 100, or 1.07. On the flip side, if we're going down, then it's going to be 100 minus x. So down x% is just going to be b equal to 100 minus that percentage over 100. So you're basically showing this change in percentage as a value that's around 1. So for example, if we went down like 14%, our b would be equal to 1 minus 0.14 or 0.86. Okay? So that'll be helpful for any percentage-related questions you guys come across. So the next video is optional about slope and the distance formula. I do know you have one question that deals with it in tonight's individual work, so I would recommend looking at it, especially if you're getting stuck on that question. Actually, let's check out which question it is. I think this is going to help out with 210 actually. So you're going to have a slope and you're trying to find another value, and we're going to try to find the distance between those 2 points as well. Okay, so we got our linear equations, linear functions, quadratic functions. We talked about exponential functions, looked at the general form, did an example, got some x's and y's, noticed that it's a constant multiplier, and then did some percentage calculations.